Welcome, everybody, and thanks for tuning into Chem. And we are in our discussion of acids and bases, and let's jump right to it, okay? Consider HOH, water, reacting with water. So I have water and water, and they're going to form hydronium and hydroxide at 25C. Is water an LB acid or an LB base? Okay, you guys remember that stuff about LBs? Last time we were talking about acids, right? And we talked about some properties and we talked about some definitions. And we said, hey, we have the Arrhenius definition, and an acid is something that increases the H plus concentration. Although when we're talking about reactions with water, we more frequently talk about it increasing the hydronium concentration. Good. And we said a base then is what? Something that increases the hydroxide concentration when dissolved in water, both of these when dissolved in water. And then we talked about Lowry-Bronsted, right? And we said that a Lowry-Bronsted acid is what? It is something in a reaction which donates a proton, right? And what's a proton? A proton is nothing but H plus. So it is a proton donor. And the base then in a reaction is the proton acceptor. Donates proton, accepts the proton. Good. So let's go back and look at our reaction and see if we can figure out what's going on. Somehow one of these waters goes from here to here. How did that happen? Well, this H, or an H here, is donated to that, meaning this is my proton donor, so it is a acid. This accepts the proton, so it is a base. And so what do we have here? Well, we have HOH, which is acting as an acid, and we have HOH that is acting as a base. Yikes. Yeah, in this reaction, water acts both as a Lowry-Bronsted acid and a Lowry-Bronsted base. Cool. Write the expression for K. Okay, well, look at this. This is an equilibrium, right? It's a little messy here, so let's clean it up. But this is an equilibrium. And if it's an equilibrium, what do I always have? I always have an equilibrium constant. And my equilibrium constant is what? The products raised to their coefficients divided by the reactants, but I only look at aqueous and gas, right? So my K in this case is equal to the concentration of my hydronium times the concentration of my hydroxide. Good. And this K is so important to us that we actually give it a subscript, and we call that KW. And maybe we should go back here and let's add some notes to this, because this is really important stuff. Let's come over here and let's talk about the auto-ionization of water. And that's what we have reacted there, right? Water plus water is in equilibrium with hydronium plus hydroxide, right? Liquid, liquid, aqueous, aqueous. Good. And this is what we mean by the auto-ionization. Auto meaning self, that water self-ionizes into hydronium and hydroxide, and that there is a K related to that, and that K is equal to, since it's an equilibrium, right, the hydronium concentration times the hydroxide concentration. Now, most things that we talk about, well, not most, but many things that we talk about in chemistry occur at about 25 degrees C, which is roughly room temperature. And so at 25 degrees C, we know, we've measured this, that Kw is equal to 1 times 10 to the minus 14th, which means at 25 degrees Celsius, the concentration of hydronium times the concentration of hydroxide equals 1.0 times 10 to the minus 14th. Now, let me say something about this. This is a big deal. And why is it? What we're saying is for any aqueous, what does aqueous mean? Dissolved in water. For any aqueous solution, at 25 degrees Celsius, the concentration of hydronium times the concentration of hydroxide equals 1.0 times 10 to the minus 14th. Yipes, minus 14th. That's a big deal. All right, we use that a lot. Now, last question on this. Oops, yoink, yoink. Better put my pen down. There we go. Yep, yep, yep. There we go. Write the expression, we've done that. What are the hydroxide and hydronium concentrations? Okay, let's go back to our notes. Had to see what I had to talk about here. Now, if you know a little bit about equilibrium, which you know a little bit, but not enough, there's a way for me to figure out what each of these are at 1 times 10 to the 14th. And what we find out is that at 25C, for pure water, that's not right. Zoink. What we do know is for pure water, this is true. My hydroxide equals my hydronium. So when I substitute that in here, what do I get? I get hydronium times hydronium equals 1.0 times 10 to the minus 14th. And so that means what? I take the square root. So that means hydronium equals 1.0 times 10 to the minus 7th molar. And if that's equal to hydroxide, then hydroxide's the same, right? 1.0 times 10 to the minus 7th molar. And this is true for a neutral substance at 25 degrees Celsius. Got it? Okay, now don't worry about how I derive that, because I really didn't show you the derivation, yikes. But later in AP Chem, we'll talk more about that. What's important to know is for a neutral substance, for pure water, which is a neutral substance, at 25C, my hydronium and my hydroxide concentrations equal 1.0 times 10 to the minus 7th molar and 1.0 times 10 to the minus 7th molar. Good. Moving on. All right, consider an aqueous solution. So I have an aqueous solution, cool. At 25C, that means I know something, right? If it's an aqueous solution at 25C, what do I know? I know that my hydronium concentration times my hydroxide concentration equals 1.0 times 10 to the minus 14th. Good. They tell me what my hydronium concentration is. Good. And then they want to know my hydroxide, piece of cake, right? What do? I substitute 5.7 times 10 to the minus 4th molar times my hydroxide concentration, now we can drop the molar, equals 1.0 times 10 to the minus 14th. Let me get out my handy dandy TI-30XA. Not quite as nice as my old HP12C. 1.0 times 10 to the minus 14th divided by 5.7 times 10 to the minus 4th. But it works very well, and I get my hydroxide concentration equal to 1.75, but rounded to 2 sig figs, 1.8 times 10 to the minus 11th. Woohoo! Molar. That is my hydroxide concentration. Is this acidic, basic, or neutral? Okay, let's add some more notes here. Na 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 na. And na 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 na. Let's talk about the, what do I want to call it? The acidic nature. The acidic nature of solutions, or characterizing the acidic nature of solutions. Okay, we'll call it that. Good. Well, we can have three things, right? I can have something that is acidic. I can have something that is basic. And I could have something that is neutral. All right, and this really depends on our hydronium concentration relative to the hydroxide concentration. As we said earlier, when my hydronium concentration equals my hydroxide concentration, we have a neutral substance. An acidic substance is going to be one which my hydronium has a greater concentration than my hydroxide, and a basic is going to be where I have more hydroxide than hydronium. Okay, cool. Now, that's in general. We can also talk about things specifically at 25C. So at 25C, I can say that my hydronium concentration must be greater than, do you guys remember? Down here we said what? At 25C, what are these guys? At 25C, my hydronium concentration equals my hydroxide concentration, which equaled what? 1.0 times 10 to the minus 7th molar. Good. What does that then, what does that mean for something that's acidic? That means my hydronium concentration must be greater than 1.0 times 10 to the minus 7th molar, which means my hydroxide concentration for a base is greater than 1.0 times 10 to the minus 7th molar, right? But we also know more, right? Because there's a relationship between hydronium and hydroxide, so that means my hydroxide concentration has to be less than 1.0 times 10 to the minus 7th. So these guys are all acidic, right? Now these two are at 25 Celsius, right? Down here, my hydronium must be what? If it's going to be basic, it must be less than 1.0 times 10 to the minus 7th molar. And once again, this is at 25C, these guys are, right? This is all the time, always. Got it? Ooh, man, looks pretty. Sign that, right? Here we go. Let's answer the question. Is this acidic or basic? Well, let's check out my hydronium for an acidic. What do I have? Hydronium is what? Greater than 1.0 times 10 to the minus 7th. So let's compare. My hydronium is 5.7. 5.7 times 10 to the minus 4th is what? That is greater than 1.0 times 10 to the minus 7th. So that means this is, oops, acidic. There we go. Woohoo! I like this pH stuff. Whoops, it's not pH. This is just acid-base stuff. All right, you do this. Bring me back when you're ready. Same idea, right? We have a solution, an aqueous solution at 25C. That means hydronium concentration times hydroxide concentration equals 1.0 times 10 to the minus 14th. Woohoo! I did do that right last time, times 10 to the minus 14th. Okay, just want to make sure. Times 10 to the minus 14th. I have a hydroxide concentration, so I want to substitute here. So hydronium concentration times 2.5 times 10 to the minus 3rd equals 1.0 times 10 to the minus 14th. Let's do some division. And what do I get? Handy TI 30x. 1.0 times 10 to the minus 14th divided by 2.5 times 10 to the minus 3rd equals 4.0 times 10 to the minus 12 molar. By the way, if this were a really smart board, I wouldn't have to use a calculator. The board would actually know what I'm writing, and I could just say, hey, board, calculate that. And it would say, okay, Kendall, your answer is 4.0 times 10 to the 12th. That would be a smart board. Okay, cool. So my hydronium is 4.0 times 10 to the minus 12th. Is it acidic or basic? Well, let's find out. We said it is basic if my hydroxide concentration is greater than what number? 1.0 times 10 to the minus 7th molar. Well, what was my hydroxide? Well, 2.5 times 10 to the minus 3rd. That is indeed greater than 1.0 times 10 to the minus 7th. So this thing is basic. Yeah. Yeehaw. Cool. Moving on. Consider a solution of HCl, good, at 25C, great, in which the hydronium concentration is perfecto. What is the pH? Aha, I tipped my hand, didn't I? And the pOH of this solution. Well, back to the notes. We want to talk about pH and POH. Ooh, where do we draw the line? Let's go far right, okay? We're gonna go this way. Hey, I heard this morning that they were thinking that you could use Tetris to help people with lazy eyes because uh, if you get both eyes working hard, then that'll make that muscle get better. And so you could play Tetris, and one eye watches one set of blocks, and one eye watches the other set of blocks, and you'd get rid of your lazy eye. Yeah. Where did that come from? Well, I was thinking about the song, the Tetris song, do 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 do, or something like that. And there we go, pH and POH, right? What are we talking about here? Well, these are very important to us, and let's first talk about pH. And what's a good definition? pH is, for me, a measure of hydronium concentration in an aqueous solution. Woohoo! Cool. That is pH. Now, how do I calculate pH? pH is equal to the negative log of my hydronium concentration. It is that simple. Great. What is POH? Well, POH is going to be what, do you think? Well, it's a measure of hydroxide concentration. By the way, this is a small p, big OH. It is a measure of hydroxide concentration, and that's not a negative, of course. POH equals a negative log of my hydroxide concentration. Got it? Okay. Now remember, pH and POH are both logarithmic scales. Do you guys remember your math? If I take the log of 10 to the fifth, what's the answer? 5, right? So when I'm taking the log, I'm really looking at exponents. So when we're looking at a difference between a pH of 1 and a pH of 2, that is a 10 times difference. Got it? A difference of 2 is 100 times. So always remember that these are log scales, and small changes in pH are big changes in hydronium or hydroxide concentration. Also, another thing, there's a negative sign here, right? So that means as my hydronium concentration goes up, my pH goes down. And so there's an inverse relationship between pH and hydronium. And we might as well get into that right now then, right? Before we go over there, let's talk about how we can look at pH and back to our question of acid, acidic, basic, and neutral. So how do we use these guys? Well, if my pH equals my POH, then that is neutral. Got it? If pH is less than POH, then it is acidic. If POH is less than pH, then it's basic. Got it? Now, in all honesty, these guys are not very helpful for us. What is very helpful for us are the numbers at 25C. This is what we use all the time. And what we say is, it is acidic if my pH is less than 7, or my POH is greater than 7. It is basic if my pH is greater than 7, or my POH is less than 7. And it is neutral if my pH equals my POH equals 7. Now, notice, I don't say anything about pH has to be between 0 and 14. That's not true. It can be, pH can be negative, pH can be greater than 14. So if you've been taught that, they were oversimplifying things. It's not true. One other nice handy thing is pH plus POH, and this is once again at 25C. pH plus POH equals 14. So if I know pH, I can always calculate POH or vice versa as long as I'm at 25C. Got it? Woohoo! I think those are all the notes for the day. We can now bust through these questions. All right. Solution 25. Okay, that means hydronium concentration times hydroxide concentration equals 1.0 times 10 to the minus 14th. I know what my hydronium concentration is. Let's calculate. Oh, I guess I don't need to do that. It says, what is the pH? Woo, I'm working too hard. What's pH? pH is equal to negative log of my hydronium concentration. Hey, donkey, they already gave you that. It's right here. So I just do what? Yoink, drop that in there, and I'm going to say that pH is equal to the negative log of 1.7 times 10 to the minus 2. Oh, doggone, we're going to have to take notes again. I just remembered something. Well, let's run the numbers here. 1.7 times 10 to the minus 2. Take the log of that. Take the negative log of that. And my answer is 1.76955. Ay, caramba. Okay, now you know what the next question, the next bit of notes are. How do I figure out sig figs? Zoink. Let us talk about sig figs here. Let's go to our notes. Beautiful, beautiful notes. Let's come down here and let's talk about sig figs with pH. Sig figs for pH calculation. Okay, here's the rule. The number of decimals in the pH number equals the number of sig figs in the concentration number. Got it? Number of decimals in the pH equals the number of sig figs in the concentration. Good. Well, how many sig figs did I have in my concentration? Well, I have 1.7 times 10 to the minus 2. This does not matter with sig figs. Here are my sig figs. How many sig figs do I have? 2. So what does that mean? I have to have 2 decimals, and so I have a 1.77 answer, right? Is this acidic, basic, or neutral? We go back to our notes. What did we say? Right, the important stuff. When pH is less than 7, it is acidic. This is 1.7. Wow, that's very acidic. Got it? Great. You all try this one. Well, we're given what? Hydroxide concentration, and they want to know the PO. Oops, did I have to do pH and POH? I'm not done here. Oops, sorry, gotta go back. Man, I'm getting too much ahead of myself. How do I get my POH if I have my pH? Well, remember, I said pH plus POH equals 14 as long as I'm at 25C, and we're always going to assume that, folks, unless stated otherwise. So my pH is 1.77 plus POH equals 14. That looks to me like I get a, what, 12.23, 13, 14 for my POH. Sounds like a winner, ladies and gentlemen. Just to make sure, 14 minus 1.77, woohoo, 12.23. Notice no units on pH or POH. Great. Now you guys do this one. I think you have, because you brought me back when we were ready to answer this. POH equals negative log of my hydroxide concentration. So POH is going to be equal to the negative log of 9.45 times 10 to the minus 8th. Okay, here's what I'm going to do. I'm going to take 9.45 EE negative 8. Good. So that's 9.45 times 10 to the minus 8th. Hit the log, hit the negative, and I get 7.0245. Well, how many sig figs did I have here? I had 3 sig figs. So what does that mean? I need to have 3 decimals. So my answer is 7.02 what? 5. I'm going to round that up. 7.025 is my POH. So what's my pH? pH is going to equal 14 minus my POH. So this is 14 minus 7.0245. And what does that equal? How about 6.975? Wunderbar. Got it? Now, is this acidic, basic, or neutral? Well, my pH is greater than 7. Excuse me. My POH is greater than 7. My pH is less than 6. Less than 6. Oy, oy. My pH is less than 7. Hey, what happens? What does it mean if my pH is less than 7? Let's go back and look. pH less than 7. It is what? It is acidic. Just barely acidic. Yes, it is slightly acidic. Cool. 2 more slides and we'll call it off. All right, a solution with a pH of 5.27. What are the hydroxide and hydronium concentration? Well, this is a piece of cake, right? We know pH equals negative log of hydronium concentration. So that means 5.27 is equal to the negative log of hydronium. Okay, that looks easier than it is. But it will be easy once you understand how to do this. Let's talk about how to go in reverse here, right? How do I determine hydronium given pH? Okay, how do I do that? It's pretty simple. Here's what you do, right? pH is equal to the negative log of my hydronium. So let's multiply both sides by -1. So negative pH is equal to the log of hydronium. Let's take the anti-log of both sides. So we want the anti-log of negative pH equals my hydronium, and that's how you do it. Now, some of you may not know what the anti-log is. Here's what it really means. Hydronium concentration is equal to 10 to the minus pH. There you go. Put that in your calculator, and that will give you the answer, right? Now, sig figs. Remember, the number of sigs in my concentration is equals number of decimals in my pH or POH, right? And just to show you the parallel, hydroxide concentration is equal to 10 to the minus POH, right? So those are the two biggies. Here's my sig figs. Let's finish this lecture. All right, here we go. Concentration of hydronium equals 10 to the negative 5.27. Good. 5.27 negative. I take the 10 of that. It looks to me like I get 5.37 times 10 to the minus 1, 2, 3, 4, 5, 6, 10 to the minus 6. But how many sig figs? I have 2 decimals here. That means I have 2 sig figs. 5.4 times 10 to the minus 6 molar. Good. Now, that is my hydronium. So how do I get my hydroxide? Well, there's a number of ways. Let's do the easy one, right? We know that hydronium times hydroxide equals 1.0 times 10 to the minus 14th. Let's drop my 5.37 times 10 to the minus 6 times my hydroxide equals 1.0 times 10 to the minus 14th. And so what do I get? Let's invert times 1 times 10 to the minus 14th. And I get 2. I don't think that's right. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the minus 9th. And it looks like 1.9 times 10 to the minus 9th. Does that make sense to me? 1.9 times 10 to the minus 9th is almost 10. It's almost 2, 10. Yeah, I think that's about right. Let's just go back and check. 1.9 times 10 Yips, 1.9 times 10 to the minus ninth times 5.37 times 10 to the minus 6, and I get 1.02. Yeah, rounding, that would be correct. And I already rounded that to 2 sig figs. So you guys all follow how I did that. Great. Woohoo! Last one for the day. You guys do this. Bring me back. Hey, I have a solution with a pOH of 3.5. I want to get my hydroxide, piece of cake, right? La 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 la, right? We know that. No, that's all wrong. We know that this is the right stuff, right? 10 to the negative 3.55. So let's take 3.55 negative, and I want to go find out 10 to that, and I get something like 2.8. How many? I have 2 decimals, so I can only have 2 sig figs, times 10 to the minus 1, 2, 3, 4. 10 to the minus 4. Woohoo! All right, now let me show you another way to figure out my hydronium. Well, what do I know? I know that 14 is equal to pH plus pOH is if I am, we're assuming this is at 25 Celsius. So 14 is equal to pH plus 3.55. So my pH should be equal to what? How about 10.45, right? 10.45, 14 minus 3.55. Yeah, I think that's 10.45. So that means my hydronium concentration is equal to 10 to the negative 10.45. So negative, and I get something along the lines of 3.5 times 10 to the minus 11th molar. And now let's just see if this works out. I'm going to multiply these two numbers together. What should I get if I multiply these together? Well, about 1 times 10 to the minus 14th. So times 2.8 times 10 to the minus 4th. And I got essentially, yeah, 9.9 something times 10 to the minus 15th, which is approximately 1 times 10 to the minus 14th. It works. All right, that's it for the day. See you next time.